The experiment is very simple. Usually the time taking part is to set it up. You have studied Michelson interferometer?
Yes, sir.
Okay. So this is a Michelson interferometer. You have a source of light here, and then you split the light into two, okay, using this beam splitter, and then the reflected beams merge. On the screen you see a pattern. Why do you see that pattern? What is the type of beam which is produced by a good quality helium neon laser? What are the optical properties?
Coherent.
Okay, reasonably coherent. And
6.
what about the wavefront? Is it a plane wavefront, cylindrical wavefront, spherical wavefront? What type of wavefront? Huh? What is Gaussian? It's a Gaussian intensity profile, not wavefront. Spherical. Anybody? It's a plane wavefront. But then, if it is plane wavefront, why it is called a Gaussian beam? What is the meaning of plane wavefront?
Shape of the wavefront. Of its movement.
What is a plane wavefront?
It propagates like perpendicular to, it's like planes. The propagation
Yes,
of wave is
at any
perpendicular.
instance, if in an electromagnetic wave at any location, if you see the direction of propagation, there is a plane perpendicular to that direction of propagation where electric field and magnetic fields are. So that is true for everything. What is a plane polarized? This is polarized. It's a plane wavefront. What does it mean?
The common tangent for all the wavelengths is a straight line.
Common tangent for?
All the wavelengths, secondary wavelengths.
Maybe you're right. I didn't understand.
I mean, every point on the wavefront is a source. It's a surplus source.
Okay.
The common tangent to all of them is a straight line. That's why it's a planar wavefront.
I think he's saying the same thing, perpendicular.
So we trace like the wavefront, like a plane wave, we cannot find an initial point.
Can you give me an expression for electromagnetic wave? Standard plane wave?
E naught e to the power of
E power I kx minus omega t.
Okay, x is the direction of propagation, and E naught is a vector.
Yeah.
It has to be a vector,
Amplitude vector.
right? But in this equation, there is only time dependence and x dependence. Where is y and z?
It can be made. It can be written
Where
in the
in the phase?
in the phase factor also and amplitude
Are you
factor.
sure? I am taking a wave
No,
which
no.
is traveling
In
only
the-
along x-axis.
For the planar wavefront, na?
No, I am choosing a wave
Okay.
which is traveling along x direction.
Okay.
For my life,
Yeah,
to
okay.
keep simple. That's all. Now, where will you put the y and z dependence?
You know.
E naught. Why? What does it give?
Electric field and magnetic field direction.
Somebody said Gaussian, no? अभी जवाब दो ना उसको. No, what does it give? Y and is E not being dependent on y and z? What does it tell you?
Intensity of the.
It is the intensity profile of the beam. So beam is traveling like this. If you take this is x-axis, y and z. If you scan the intensity, that is the strength of electromagnetic field, is changing along y and z. That is going to give you the intensity, the shape of the beam. Then what is plane polarized? If you take a plane perpendicular to the direction of propagation and take every yz point, any yz point, the electric field will be pointing in the same direction at any instant of time, and the phase of that point, phase meaning with respect to to E0 of that point, every E0 has it, every y and z point will have its own E0. That's what gives you intensity profile. Correct? Every This is the beam direction. Beam is most intense in the center, less intense in the outside. So if I scan along y-axis like this, the intensity will go up like this and come down. So at every point in this plane, there is a E0. And with respect to its E0, at that point, the electric field will be changing its magnitude sinusoidally. Correct? So, when you have a plane wave or plane wave front, what does it mean? You take this plane perpendicular to the direction of propagation. At every point on the plane, the phase is identical.
A plane of constant phase.
No, a plane need not always be the plane of constant phase. For example, if you had a spherical wavefront,
Okay.
then a plane will not have constant phase. A sphere will have a constant phase. Yes? Okay, very good. So if it is a plane wave, will you get interference fringes like that?
It was plane wave, son.
Then?
That's why we are getting interference.
No. Will you get? Remember, I told you, on a single plane, the phases are identical. If that is the case, when the wave meets this plate, you understood, no?
Okay.
All of them will have the same phase. So there are two waves coming, one coming from this mirror, one coming from this mirror. So when they merge together, they will merge depending upon their phases and they will give you interference.
Okay.
Either bright or dark. Right? But it should be bright or dark all over the plane. But it is not. It gives you fringes. Why?
So it's because of the lens.
Exactly. What does the lens do?
It makes it spherical.
Spherical. And if you have this spherical wavefront, then why do you get fringes? I told you spheres will merge like this.
So similar interference happens. Some intensity gets more damage. Addiction.
The sphere has to reach there. Spherical wavefront. The center of the sphere is decided by the optical distance between the lens and the plane, screen. Yes? But that includes mirror and the beam splitter. If this mirror is closer to the beam splitter, this wavefront will have a smaller radius sphere. This wavefront will have a larger radius wavefront. So it is like two spheres, two spherical wavefronts, but their centers don't match. If their centers don't match, can you imagine two spheres intersecting each other, but their centers don't match? So then you will have rings of certain phase relation. That's why you get that.
Sure.
Okay.
This is a plane and a spherical wave.
No. Both are spherical.
They're both interesting.
The lens is placed before they meet here to the beam splitter. That means from here onwards, the plane is no longer a plane. It has become a spherical wavefront and it is traveling. So it will travel as a spherical wavefront, meet this beam splitter, split into these two, come back and hit the screen. They are still expanding like a spherical wavefront. Understood? Okay, fast.
Sir, so eventually the spherical waves are making a planar wavefront.
No, there is no planar wavefront after the lens. It's like you have spheres making interference and then you are cutting it through a plane. That is this plane. That's why you get rings. If this screen was a spherical ring screen, you wouldn't see this.
Like it was a spherical screen?
Then you will see just a distribution of light, uniform distribution of light.
So what do you mean by centers are different?
This is now a spherical wavefront, right? So if you take the curved sphere and project its center, correct? There are two wavefronts which are meeting there because there are two mirrors here. But if these two mirrors are not having exactly same distance from the beam splitter, then one will be a sphere with larger radius, another one will be a sphere with smaller radius. And now you have kept them together on a screen, right? So they are kept one inside the other, their centers don't match. But this wave front is matching, no? Because that's why you can see all of them together. So when you cut it, there's a plane, you see rings. Okay, now what is going to happen? If you move one of the sphere with respect to the other, these fringes are going to move. So what we have done here is we have mounted one of the mirror on a nickel rod. That nickel rod is passing through this coil and we will give power to this coil. क्या है इसको
Start
और नहीं दिया इसको ना नहीं हो सकता है इसका फ्यूज गया हो। ओह इसमें फ्यूज है ही we need a fuse for this. Run through this coil, what happens?
This will move, sir.
Huh?
This will be moved.
Remember,
Force.
this rod is anchored with this bolt at one end, right? So now it is held here, no, using this screw tightly. So now you have this nickel rod standing like this. There is magnetic field here and the mirror is standing here. You put magnetic field, this mirror moves. Why does it move?
The rod moves, sir.
Microscope. Why the rod should move? It is held physically. It cannot go anywhere. The rod doesn't move. It contracts or expands. Why does the rod contracts or expands? Microscopically, what happens?
Vibrations.
Huh?
Vibrations.
So magnetic field is
Frequency electro.
Vibration is periodic. It's a DC movement. Huh?
magnetic field.
Inside the
So what do they do to the mechanical structure?
if they align,
So that is all fine. Why the mechanical change happens? You are talking about magnetic domains and magnetic change. That is agreeable. Why mechanical change happens?
Sir, the magnetic field is applying force on the atoms. So atoms are getting dragged.
That force is not going to do anything.
So it's producing heat inside.
Okay, the phenomena is called magnetostriction. We will discuss again sometime what happens, but something very interesting happens. At the level of the electronic structure of the atom, something happens. And have you done quantum mechanics, or you going to do quantum mechanics, or you doing quantum mechanics?
Doing, sir.
By the end of this course, you will learn something. You are not going to learn this in quantum mechanics, don't worry. But you are going to learn something called perturbation theory. So this is actually one of the
Actually learning.
application. Huh?
Actually learning, sir.
Perturbation theory शुरू हो गया already.
Time dependent. Atomic and molecular.
When did you do your first quantum mechanics course?
Last sem.
That is why. So you didn't study time independent perturbation theory.
We studied
Now, this,
Time independent you are studying.
we studied 1 week last.
Time independent. So it's related to that. During the experiment, just make sure that you get very stable fringes. That is very, very necessary. If one of the mirror is slightly loose or something, this will cause problem. And you have to take the reading very fast. What you have to do is you have to apply current through this. We will give you a multimeter. You will know how much current you are passing. As you pass the current, the magnetic field will change the mechanical structure of this nickel rod and the fringes will move. The central fringe will go from dark to bright, bright to dark. How much wavelength change has to happen to go from bright to dark? Lambda by 2? Yes. In this case, it is lambda by 4. Why? Because it's a mirror twice. Okay. So when the rod moves by lambda by 4, the effect on the screen is equivalent to lambda by 2. Okay. So by counting the number of fringes changed, you can count how much expansion and contraction has happened. And remember, the wavelength we are using is 630 nanometers, less than a micron. And you're talking about a change of several lambda. Okay. And you can see it in steps of lambda by 4. That means you can see 0.1 micron change in the length of this rod as you pass the current through this. So it's an extremely sensitive technique. Okay. You understand? You know, one of the places, there are several places this technique is used. One of the places here it is used is in Large Hadron Collider. You have heard of Large Hadron Collider? The circumference of Large Hadron Collider is 27 kilometers. There is an airport in the middle of that accelerator. Okay, it is that big. Okay. Now the problem with that is the full accelerator cannot sit on one bedrock. It's not possible. So obviously it is on pieces of rocks underground. It's almost like 50 to 100 meters down. Different level places it is different height, but it's 50 to 100 meter depth. There is a tunnel of 27 kilometers circumference, and the accelerator sits. You know what is the size of a proton beam? It uses 7 tera electron volts proton beam going one way, and 7 tera electrons of anti-proton beam going the other way, and then they are collided. Okay, the diameter of the beam is 35 micron, size of the hair. Can you imagine one 35 micron hitting another 35 micron at the speed of light, almost at the speed of light, at a distance of 27 kilometers, and not once, again and again and again, every second 10,000 times. 35 microns at 27 kilometers, right? Now imagine buildings keep moving. You see this building is made out of 3 pieces. How many of you have noticed that? You didn't notice it. When you walk from here to the center hub of the staircase, you will see that between the two there is this thick gap which is filled with rubber sheet. Yes. Now today when you are going back, you see there is this thick. The place where there is the staircase, main staircase, that hexagon is disconnected from this part of the building with this much gap, and it is filled with rubber. The other side also the same. And if you actually take sellotape and take one of your hair and put it and stick it, there is no guarantee that it will be intact tomorrow. The differential change in this can actually break it. Okay? It moves. That's not a big deal. Few microns per hour is not a big deal for Earth. If your building is not standing on the same bedrock, even on the same bedrock there will be small movements. Now you're talking about 27 kilometers circumference, right? Accelerator inside ultra high vacuum tube at ultra low temperatures, and it is doing this all the time, and then on this 35 micron has to cross another 35 micron. Okay? Yes? It is like you are standing inside, not sitting in the plane. You are standing in the plane. The plane is flying in a hurricane, and you have a needle and a thread, and the lights are off, and you have to now do this. Okay? It's worse. So now how do you make sure that the whole thing is aligned? You use this. The full accelerator system is mounted on blocks, very thick legs. Underneath each leg there are piezoelectric drives and a beam of laser interferometer going. If any of the structure moves even by a micron or less than a micron, a feedback circuit sends voltage across the piezoelectric crystal, and the whole structure is dynamically corrected. Okay? Because this reaction keeps happening for months, if not years. There is no time to stop and correct it. Okay? So interferometry is very interesting technique, very useful. You can do such ultra sensitive measurements. How many of you notice that the central fringe has become dark from bright? You know why that happened? If I move from here, after some time it will become bright. If I again come here, it will become dark. My body heat is changing the temperature there.
So much sensitive.
It's interferometry. You're talking about 100 angstrom change, 1000 angstrom change. That's not a very large change. It's a very tiny change, but the technique is quite sensitive. Let's come here quickly. I have to go by 4 o'clock. This experiment is something which again you have already studied. This is called Zeeman effect. How many of you have heard of Zeeman effect? So what we have here is an electromagnet, and if you look through this hole, you will see bright bluish green light inside this. Okay, you can see it from this side also. That is a lamp, it's a cadmium lamp, and this power supply is actually operating that lamp. The cadmium lamp emits characteristic light of cadmium, and which is bluish green. What we do is we put this red filter. You see, this is the actual light. Okay, we put this red filter and make sure that that bluish green part is removed from the spectrum. Okay, we only see red. What we have inside this box is called a Fabry-Perot echelon. It's basically two glass plates, semi-transparent or partially transparent glass, or say partially reflecting, mostly transparent, partially some 95-96% transmitting plates, so that a small amount of light reflects between the two plates, and this reflected wavefront and incoming wavefront, they interfere and you get fringes. Again, because there is a lens in front. If there was no lens, you will get a plain wavefront. Here there is a spherical wavefront and you get fringes. These fringes are then focused onto this camera and you can see those fringes on the screen. It's as simple as that. But this lamp is kept in the presence of these electromagnets. Okay? Now we are going to look at what happens when I apply magnetic field. So before applying any magnetic field, we have very nice rings and you can see all the rings. And now I am going to put some magnetic field and you see each of the rings became 3. Okay. Can somebody turn the knob please so that we can dynamically see this change happening? Make it 0 fully. Okay. Increase, and you can see, make it 0 again. We don't want to heat the coils. Even there, when you operate that experiment, when you are scanning the current, you have to do it very fast. If you keep the current on for some time, the coils will get heated and then the thermal effects will start expanding and contracting the rod, and that is not good. So the way to take the reading is take your mobile phone and record a video where you keep the multimeter and the screen in the same frame and you rotate the knob on the power supply. The current will go like this and the fringes will change and then reduce the current back. Within 10 seconds your experiment is over. Then another 15-20 minutes to change the rod to copper and iron. There are 3 rods. You have to do the experiment with 3 rods. Okay. The only time consuming part in that experiment is essentially alignment. Okay. Then after taking the scan, all you have to do is look at the video, stop the frame whenever there is a fringe change from bright to dark, note down what is the current value. How many changes? Bright to dark, 1 bright to dark, you call it +1. And it can do reverse also. It initially will expand. That's another beautiful thing which will happen. Initially it will, in one case, I will not tell you which one, it will initially expand and then start contracting. So please give, when it goes from bright to dark, you can remember the sequence. You can see it in the video. Bright to dark, dark to bright, bright to dark. If that is the sequence, okay, you give +1, +2, +3, +4. When it reverses,
bright, dark to bright.
Okay, bright to dark देखोगे तो dark to bright ही आएगा ना उसके बाद, right? But you know how it in which sequence it went.
Yeah.
Okay, how will you know that? Bright to dark हो गया, dark to bright हो गया. Before the color changes or the intensity changes, the rings will move in or out. Okay, when the central fringe becomes dark, the outer fringe will actually either come in or go out. You understood? You understand? What will happen? Central ring, bright, black ring, dark ring, and then there is another bright ring. As it diminishes, as the central one diminishes, there are 2 ways in which it can diminish. One is this contracts. Other one is it expands. Understood? So you give your own sign convention, one positive, one negative. Later on you think, if the rod is expanding, should it do this or it should do this, and so on. Okay? And then accordingly you give number. Here on the other hand, the fringes don't collapse, they simply split. What is actually happening? If you are getting these rings, what does it mean? You have one wavelength which is being emitted. When you apply magnetic field, each fringe becomes 3. That means that has become 3 wavelengths. Why this happens? Because of the magnetic field. What does the magnetic field do?
Loss of degeneracy.
It lifts the degeneracy. So the transitions are between an S state and P state. Okay? Because of delta L plus minus 1. Or P state to D state. Right? So you can have transition between S and P, or you can have between P and D. In this case, it is between P and D. And now you sit down and calculate how many possible combinations you can have. D orbital has 5 substates, right? And P orbital has 3 substates. And what are the selection rules? Delta L has to be plus or minus 1, and delta ML has to be plus or minus 1 or 0. You understand what I'm talking about? Right? Clear? So now you sit down and find out how many combinations are possible. Okay? So of course there are 16 combinations, 18 combinations which are possible. Okay. Actually 9 combinations, but spin half and 18, but let us say 9 combinations are possible. Then I should have seen 9 transitions. If I should have seen 9 transitions, why am I seeing only 3? That means out of these 9 transitions, okay, they all 9 have been grouped into 3. Actually, if you make the diagram, you will find that they are all grouped in 3, 3, 3. This is possible if and only if the splitting between the energy levels is independent of L and ML. The splitting is only dependent on delta ML of plus 1, plus 1, plus 1 or minus 1, minus 1. That means all the energy levels where the degeneracy is lifted, it is lifted by equal amount. And that is why the energy levels will match. This was what they discovered first time. It was been given Nobel Prize because it showed a very fundamental effect that in the presence of strong magnetic field, this is possible only when you have a single electron system. Right now this is, of course, cadmium is not single electron system, but by filtering out the blue and green, which doesn't behave like a normal Zeeman effect, we have taken only excited to excited state transition. The red one is an excited state to excited state transition. It is effectively single electron system. If you take a very simple low single electron system and apply strong magnetic field, then the splitting in the energy levels is explained on the basis of normal Zeeman. It is called normal Zeeman effect. What you see now, okay, this is the actual spectrum, okay, and if I now apply this, they all get mixed. This is called anomalous Zeeman effect. Okay, the bright bluish green wavelengths, they are coming from other complicated transitions which are more strongly bound, so they have multiple electrons participating and life becomes complicated. Whereas an excited state to excited state transition is far away from the other electrons, they don't participate, only one electron participates. Okay, so the explanation of this effect becomes very, very simple. Okay, now before we close this chapter, what I will do, let me try to do that. I will try to put this polarizer in the path, and let me see how it turns out. Okay, so now we have a polarizer in the path. I hope it stays nicely like that. And let me make it fixed. Yes. And what you see now, I want you to watch carefully. I don't know if you can see, the screen is very bad. We are waiting for new computers to come. I am changing the angle of polarization, and you can see that out of the 3 rings which had almost similar intensity, now only one of them is bright, the others are gone. Now I rotate the polarization to vertical axis, and this vertical axis now, and you can see the central one is gone, Okay, when I make the polarization horizontal, only the central one stays and the other two gone.
And sir, in the that first order ones, there are like outside boundary ones
Yeah,
are getting.
that will also change. Okay, so this is basically the transverse Zeeman effect. This is what we are seeing is called transverse Zeeman effect. You know that the magnetic field is applied like this. So those transitions where the dipole moment is along this axis, along the parallel to the B axis, is not affected. So those rings remain where they were as if there is no magnetic field. But the ones which are perpendicular to it, they are affected. But depending upon which way, this is the magnetic field. If the electron is moving like this is not what the explanation was given. Zeeman actually discovered this effect, and Lorentz, okay, gave the explanation. Who was Lorentz? The guy who discovered Lorentz force, and he was Zeeman's boss. So he gave a simple explanation on the basis of Lorentz force, which is not correct, but it answers the question very nicely. Though there is no actual electron rotating like this, but you can have this wrong model, but the answer is correct. So basically what he said is, imagine you have magnetic field like this and some atom having its electron going like this. So the electron is oscillating like this. So when it emits, that radiation is unaffected by magnetic field. But the electron which is going like this is like a loop of current, right? So it's like a dipole. So the dipole, if it is going like this, the dipole is pointing opposite. If it is going this way, it is pointing opposite. So the potential energy of this configuration, for this configuration there is no change in the potential energy. This configuration, it is more potential energy. This configuration, low potential energy. Therefore the energy levels shift and you get two rings extra, one inside and one outside. That is how this effect was explained. It's a wrong explanation, but the answer is correct. In fact, even the formula gives the correct answer. It's actually not the case. If you put quantum mechanics, you get more accurate and the correct answer. But for now, this is what we will deal with. So you have to measure at different magnetic fields. We have a calibration graph for this. You know the current, how much there will be a multimeter, you will pass current, you will check how much that current correspond to how much magnetic field. For that magnetic field, you will measure how much is the
fringe shift.
You have to take these pictures. The screen is bad, but the pictures are good. You can just store them using one of the knobs here, and then later on copy them in a pen drive or something. You would have noted down the current value in the picture, and you take the pixel size. Everything is in a ratio, so it doesn't matter which unit you use as long as you use the same camera. You need not use this camera, you can use directly your mobile phone also. But please make sure if you're going to use your mobile phone, it should always be in the same configuration and same camera. Because if that changes, then it's a problem. It is still not an actually big problem because there is a normalization within itself. You will be using every image and its own inner radius, outer radius, and you will be dividing. But still, it will have some skewness, and that is not good. So you try to avoid that. So you can directly capture, collect those, and take it with you. Okay? We will be changing this soon. So anyway.
Lorentz explanation that you gave, it says low potential.
Originally, without magnetic field, we were only two. Because of the magnetic field, they become this much, right? Why did they become this? And if they become like this, why their response to polarization is like this? So his logic was, if they are horizontally polar, that's why when I made this horizontal, you have the central line. When I make it vertical, you have the other two lines. So that everything fitted very well. Okay.
In that term, you can well.
Because your axis of quantization is now horizontally like this. So this corresponds to ml equal to 0, and every time delta ml is equal to 0, that will remain this, and the energy wise also it is valid. So it worked. So only later on we got a little bit better with quantum mechanics. Okay, next experiment. Damage this. Your previous batch has damaged this, that's why we have bought a new one. This is a very ultra thin window. Never try to investigate. And inside it is argon gas, which is at 40 millibar pressure, which is much less than the atmospheric pressure. So and this is a very thin window, so that radiation can enter in. And inside there is a center, there is a needle, tungsten needle, and there is a high voltage, 600 volts is applied through this box. Don't worry, you will not be electrocuted. Its current capacity is extremely low. That voltage is applied to this needle, and you have low pressure gas and inert gas. What happens is whenever the radiation, high energy radiation interacts with the wall, it produces some charged particles, and the needle is given very high positive voltage, 600 volts. So the electrons rush to the center of the needle. As they rush, their energy increases very rapidly, and then they collide with other atoms and ionize them, produce more electrons. They also get accelerated and hit other atoms, and in the process produce a large number of charged particles, and you get a very rapid pulse. It just tells you that something hit the detector. That's all. It doesn't tell you how much is the energy, whether it is an alpha particle, gamma, or what it is, or it doesn't tell you anything. It just says high energy radiation hit you. Now, this is what is used. Have you seen Chernobyl?
Yes.
This is the standard radiation monitoring device. It is designed, size and content and everything is designed in such a way that at a certain rate it represents the dose which our body is getting. See, radiation dose is a very tricky object. Okay, how many alpha particles are enough to kill a human? How many gamma rays are enough to kill a human? It's very hard to tell. Why? Because if you are irradiated with 1 million gamma rays per second and their energy is 1 giga electron volts, they will do absolutely nothing to you. Their energy is so high that most of them simply walk past your body doing nothing. But if the same intensity X-rays are used, which you use for medical, it can cause cancer, because their energy is 190 kilo electron volts. They pass through your body, but a good number of them interact with your body. Okay, now I have 10,000 gamma rays of 200 eV passing through my hand every second. If that is replaced by 500 MeV electrons, will the effect be the same? I don't know. These are different particles, they interact differently. You have to study them separately. So you needed, in those days they needed a cheap and a simple detector which can simply tell you whether you are safe or not safe. That's all matters. What type of radiation is a secondary issue. GM tube is a very good device for that. So it is directly in the small device. Actually you can build your own. If you buy this, it costs a few thousand rupees on eBay or some other places, and you can build your own matchbox size GM detector, GM counter, and you just take it around and you can connect it. It produces these high voltage pulses which can be then converted into low voltage logic pulses, and they can be fed to a speaker, and then it will do that krrr sound. If you see Chernobyl, you will know what I'm talking about. Okay, and that just tells you that whether you are close to a dangerous zone or not. Okay, but here we are going to use it to study some interesting behavior of radiation. So what you're going to do is, we have radioactive sources we will give you. First you will take it without any radioactive sources, because everything around you is radiating, including the concrete is radiating. This concrete contains potassium, and then that potassium contains a very tiny amount of a particular isotope of potassium, and that is radioactive, emits gamma rays, and that can get detected. So around us there is a lot of radiation. That gives you the background. Then you put a radioactive source like this here. It's a point source, so it is emitting in all direction, but your detector is here, so some distance wise there's some detector, some things will get detected. The source which we have, they are typically 36 kilobecquerel, that is 36,000 radiation particles per second, or 72 kilobecquerel, that is 2 times of that, and depending upon that you will get some flux, and this will count, and you have to measure the count rate as a function of distance. Then you fix the distance, and as a function of plates in between, you put lead plates, half a centimeter, 1 centimeter, 1.5, 2, 2.5, up to 7 to 8 centimeters, and you count each case for 5 minutes each, and how many counts came, because your radioactive source is almost stable. So what you get is basically what is attenuated, the rest of the material you get. So you will get an exponential function as a function of thickness.
Sir, what does this lead plate is doing?
So it is basically showing you that when you send n0 number of particles onto a lead plate, you don't lose all n0 on the other side. You lose some fraction of that. Okay. Now if I double the thickness, I don't lose double of them. I lose e to the power minus lambda T.
But
This lambda is the characteristic of the material which you are keeping and the characteristic of the radiation which you are using. The energy, the type, and so on.
But why we are using it?
For shielding,
Okay.
for application, shielding. For understanding, it's a very fundamental physical phenomena, attenuation, which we study.
So is it because lead is the most stable isotope that we have? I mean,
No, there are many other.
After every radioactive decay, after like
Not every radioactive decay doesn't produce
we have
lead.
that 4n+1, 4n+2 series, no?
No. Not everything produces lead. But the reason why lead is used is lead is most stable in its own form. The radioactive transformation of lead is very difficult to have. That is only one. There are many other elements which have the same property. Second is the density of lead. It's one of the highest, not the highest density, but one of the very high density material. That means when you keep 1 centimeter by 10 centimeter by 10 centimeter plate of lead in front of your face, you are putting a large number of lead atoms in front of you. That's the advantage. So density and radioactive stability is the reason why we use it. But it is carcinogenic, so if you don't die by radiation, you will die by cancer. So, but yes, in Roman era, people used to make water pipelines with lead. So, yes, I have seen them. If you go to a place called Pompeii in Naples, you will actually see them. Okay, so that's the experiment. This also can be used to study something called Poisson distribution, but that we will discuss later. What we have over here, this is a helium lamp. I have kept it open, but actually this is a cover which you can keep on top of it. And then we have here a grating. Okay, so first thing we do is we align this so that we get a nice view of the slit which is kept over there. Then I add this here. I still see the slit, and then I go to an angle, and you can see that different colors are separated very beautifully. I don't know if you can see it. I leave it working for next half an hour. You can actually take a look at it. What you can do, of course, is you can set this stage. You see there are angle marks here with vernier scale. You have to very accurately align this apparatus for this line and for this grating to be perpendicular. There is a procedure given. After that is done, you turn this thing like this, you measure the angle on both sides. Okay, and then you know the formula for diffraction grating. Transmission grating, what is the formula? What is the formula? N lambda is equal to
2D sine.
not 2D sine, D sine.
D sine.
This is a transmission grating. Okay, so all you need to know what is the number of lines per millimeter that is given on this is 600 lines per millimeter. So you know what is the value of D. You can find out, and then from that you can get your wavelength. You will get first order diffraction, second order diffraction. Second order diffraction will give you better resolution. Then what you do? This is helium. You will do the calibration with helium. Helium transitions we will give you. It will be written like this paper. See this? These are the helium transitions. And this is a helium lamp. So you will measure it, then you will switch it off, wait for 5-10 minutes to let it cool down. Do not touch it by hand. If you touch, your skin will stay there. I am not joking. Whatever happens to your hand is a different thing. You will not die, don't worry. But that will spoil the lamp because the skin will stay there and it will burn and it will get carbonized and it will become brown, and then after that whenever you switch on the lamp, more heat will be deposited there and at one point it will crack. Okay, so we don't want that. That's why you see there are actually, it is double walled. You must have noticed there is a glass inside the glass. Both are quartz. The outer one is also quartz, inside also quartz. But don't bank on it. Okay, after that you will replace it with sodium lamp, and you will see, and what you will see is something called fine structure effect. The sodium lamp glows yellow. This yellow line is actually very characteristic. This is called D1 D2 lines, and they are actually having a small difference in the energy. So you will not see it in easily. You will see it, but not very easily in the first order. But in second order, you will see that yellow is actually having two lines. You have to measure that small angle and calculate that splitting. And that splitting comes because of something very fundamental. Because this sodium is a properly single electron system. Its configuration is 1s2, 2s2, 2p6, 3s1. So the inside 10 electrons are tightly bound, only one outside 3s electron is jumping up and down. So 3s electron goes to 3p state and comes down. So when it comes from p to s, it emits that yellow line. So this yellow line corresponds to this transition. So you expect it to have only one energy. But because it is coming down into a state where there are two possible configurations, it can be p3 half and p1 half. Okay, and from the if you consider only first order effect or zeroth order atomic theory says these two levels should be exactly same, but the spin orbit coupling introduces a perturbation, and that perturbation splits these two, and you get a small gap. That is called the fine structure gap or fine structure effect, and that is what you will be measuring. Okay.
Like, sir, what it is creating, like perturbation is creating the split.
Yes.
But how in the orbitals we can say?
Yeah, that is because the spin dipole moment of the atom and the orbital angular momentum produces its own magnetic dipole moment. They interact with each other, and because of that, now there is some sort of a ambient magnetic field, or I shouldn't say magnetic field, but some sort of a field with that field basically affects the energy levels.
Splitting it.
It affects the potential directly. I shouldn't say magnetic field. So there is a term. You didn't study enough spin orbit coupling. Okay. So there are effects which actually shift the energy. That's called fine structure effect. It's very fundamental because this fine structure effect gives rise to a very important natural constant. What is the natural constant? You know fundamental constants.
1/137.
Yeah, but what is the difference between natural constant and a fundamental constant? Fundamental constant like speed of light depends on the value of that number, depends on the units. Natural constants are like pi, e. They don't have units. But in physics, there are very few numbers which can be called as natural constants. Fine structure is a natural constant, 1/137 point something. It's a natural constant. It's a natural unit. Okay. Anyway, you will study that. Okay. Next. Volts. Maximum up to 10,000 volts, which is fed into this. So these two plates right now are floated at 1.7 kilovolts. But don't worry. Even if you touch it, you will simply feel some jitter. You will not die. If at all you will die out of fear, not because of electric shock. Okay. Now, do not touch this thing here. Okay, because this is where the plasma is having highest density and the temperature will be high. So I don't want the tube to be spoiled again. You can hold it here, the top or bottom, when it is off. Now if you look through this grating, you will see the line, but if you watch carefully, on the right hand side and the left hand side, you will see colors, lines of different colors. That's basically why, because this line is passing through this and getting splitted into different colors depending upon the emitted wavelengths. But when you are looking it, you are projecting this back. So you can actually see these numbers and also colors on those numbers. So you have to note down what is this number and note down these numbers, so you know how much is this distance. Measure this distance using this scale, so you know a triangle now, so you can find out what are these angles, and the same formula. Okay, n lambda is equal to d centimeter, and you can find out the wavelengths. And these wavelengths are basically, this is a hydrogen lamp, so these wavelengths are
splitting ज़्यादा ही नहीं आया.
And if you remember, what is the formula for the energy levels of hydrogen? 13.6 electron volt divided by
N square.
n square. So that formula, actually if you take and convert this information, you can directly calculate the wavelengths and you can compare. From this you can also find out what is Rydberg constant.
अच्छा ये वाली ये एक
Okay. So it's basically these transitions are not transitions. These transitions are called Balmer series because the n equal to 1 state.
यहाँ पे
Okay, if you take n equal to 2 to n equal to 1, the energy level difference is 10 electron volts, which is ultraviolet, deep ultraviolet. You can't see it. So
ये blue वाली
transitions from 3 to 2, 4 to 2, 5 to 2, they become visible. So those are called Balmer series. So the first series, that means transition from higher state to n equal to 1 state, that is called Lyman series. Those are in ultraviolet, you can't see them. Transitions from higher state to n equal to 2, they are called Balmer series. They are visible. All the other transitions are infrared.
लेकिन एक blue वाले कहाँ से
Yes, done?
What are these numbers?
Huh? वही तो है. This has those transitions. They are getting spread.
Blue and
Three of
Yeah,
these.
that's why you have a lot of other colors coming, but ignore them.
so we have to compound this way.
Which is the sharp lines. You get the sharp.
पता नहीं वो record हो रहा है
Yeah, those red, the blue, the pink, the sharp lines.
मैं ड्राइव पर अपलोड कर दूंगा सबको लिंक दे
Okay.
दूंगा
Basically, you have to find out where this line is. Okay. Good. Very good.
next
The next experiment is the Fourier series. You have studied Fourier series already?
yes
Yes. Okay. So if I have a sine function here and a frequency of 1 kilohertz, I'll keep everything same. Simple. Okay. And I give that out and I show you here. This is how it looks. Hardly surprising. Same thing I can do to channel number 2 with a frequency 1 kilohertz and the same amplitude, and you can see that okay, they are nice and frequency time period minimum aligned phase.
उसके मोबाइल में दिख रहा है
Phase. Okay, so you can see that these are two identical waveforms coming from two different channels. Okay. You can do some circus with this. For example, utility display format. So what is this machine? You know. It's an oscilloscope. What does it do? It takes electrical signals and shows you the electrical variation as a function of time. So it is in YT mode. YT mode meaning
time
Y as a function of time. It also has an XY mode in which this acts as a X-axis, this acts as Y-axis. So if I go to XY mode, it will look like this because both are sine waves. Okay, but now if I give phase difference between the two, you can see that they become elliptical. If the phase difference is 90 degrees, it will become circular. If I give the phase difference the other way, it becomes 180 degrees, then it becomes a straight line but on this side, and so on. So this, because both of them have exactly same frequency, okay, only the phase difference is changing. But anyway, suppose now I demand that the frequency here is changed. One is 1 kilohertz, the other one is 1.001 kilohertz. 1 hertz difference. You see what is happening? Okay. Oh, I don't like all this. So let me make it 2 kilohertz. It is stable again. One is 1 kilohertz, the other is 2 kilohertz, but there is a butterfly. Okay. And when I change the phase, see what happens to that butterfly. Okay. This is called this phenomena. These figures, they are called Lissajous figures. Okay. Don't worry what is the name and what is the purpose of this. Someday we will discuss. Let's go back to our normal process. So one is 1 kilohertz, another is 2 kilohertz. So I will demand no, both of them should be same. Now I remove one of them. I am not interested in that right now. And this also I will switch off. Now I say, what is the Fourier transform of this waveform? You know what is Fourier transform? Yes, no?
Yes.
Okay, so we will take a fast Fourier transform of this. And what do we get here? Okay. This is my 0 here. Okay, and I have something like what? I am giving 2 kilohertz. Each unit is 1.25 kilohertz, right? So the peak is exactly at 2 kilohertz. That is because I am giving 2 kilohertz frequency. Okay, if I make if I make this 3 kilohertz, it jumps to 3 kilohertz. If I make 4 kilohertz, it goes to 4. If I make it 5, it becomes 5 kilohertz. That is because I gave a sine wave. What if I give a 1 kilohertz ramp? You know what is a ramp? It's like this. And you can see that now, not only that I have the fundamental frequency, I have omega naught, 3 omega, 5 omega, 7 omega, 9 omega. Why don't I have a 2 omega, 3, 4 omega, 6 omega?
So natural frequency is not.
Why not?
It's not a multiple.
Now it is there. Now it is not there, but if I change the symmetry, see, it's there. If I have a symmetric triangle, then it is not there. But for other cases, it is there. Can you think of a reason why?
Mathematically, it's to find the coefficient.
Mathematically तो सब कुछ होता है यार. Physically क्या हो रहा है? Okay, that time we will discuss. Okay, what will happen if I give square wave? Ooh, very bad. Huh? And this is vertical axis is log scale. Okay, it is in decibel. So you can ignore this chota grass. Okay, first, second, third, fourth, fifth. Okay. Okay, so you can see the ramp has this behavior. This is the ramp, and look at square. Okay, we will discuss why it is like this and how it behaves like this. But what you have to do now is stop this and record the amplitudes of this. You know the formula for Fourier series. You record this amplitude and check whether your numbers match or not. Okay, and then after that you can play things like this. See, we have something like, you know what function is this?
Fourier transform.
No. What is this function? It's a sinc function, sin x by x. Look at its Fourier transform. But what is the Fourier transform of sin x by x? Step function. This is not a step function. It is not a step function because for Fourier transform you have to integrate from minus infinity to infinity. Here you don't have that. You have only finite sampling. That's why you see this gap is because this fellow cannot produce only one sinc function. Then it will produce and go away. It is producing 1 kilohertz. That means it is producing 1000 sinc functions per second. Right? That's why this gap will be exactly 1000 hertz. Okay? The same thing let us do way from Gaussian. What is the Fourier transform of a Gaussian?
Gaussian.
But this is, look at this. This is not Gaussian, it is parabola. Because I told you this is log scale. Okay, so in frequency domain it is Gaussian, right? So because you have taken a log decibel, it is showing parabola. So you have to do this calculation by hand and then compare it with your results. Okay, and you can explain why there are gaps. Otherwise theoretically it should be simply a function like this, but that is because you are not giving a single Gaussian, you are giving repetitive Gaussian, so that repetitiveness gives rise to this. This is very important for quantum optics, quantum information, in general for quantum mechanics, why this kind of structure comes. Okay, now this is Lorentzian. This is exponential rising function, exponential decay function, and so on. And this is sine square, and so on. So you can play around with this, measure, calculate, compare your calculation with the measured values. In the process, you must learn how to use the oscilloscope and how to use a function generator. Oscilloscope is a very nice device. If you learn how an oscilloscope works inside out, more than half the experiments in the world you have understood. As simple as that. Once you get this logic right, you can extrapolate this logic to so many experiments that you will have no trouble understanding other experiments. You will understand them much more easily. Spend some time understanding this machine. Okay? You can actually download apps which will convert your mobile phone into an oscilloscope. Only difference is this oscilloscope can go up to 70 megahertz. This one can only go up to 20 kilohertz. Okay? But you can play. Nevertheless. Here. You see how much spectrum it has recorded already.
What is the sensitivity?
That we will see. Can I get some radioactive source? Okay, what we have here is a gamma ray spectrometer. It's basically a sodium iodide scintillator. So in this part, hello? In this part we have a crystal. It is called sodium iodide. It just looks like piece of glass. Okay. And these are radioactive sources. They are safe to handle and as long as you do not touch any other part other than this. If you try to touch this part, it is not good for your health. Okay. This one is americium 241. The actual radioactive source. No, it's not a torchlight. It is emitting in all directions. And this is emitting alpha particles of 5.3 mega electron volts, and they travel in air not more than 8 centimeters. And in our skin they stop well before they reach epidermis, so it's okay. Now the actual material, okay, she's afraid of it. The actual, do you see some brown dirt like thing? That is the actual radioactive material, and this is made in year 2007, and it is still radiating at the rate of 74 kilobecquerel, that is 74,000 emissions per second. That just tells you how large Avogadro number is.
But the rate should have decreased by now.
Small. Very.
What is the half-life?
400 something years. Okay, so now what you are going to do is you are going to use something like cobalt 60. So americium is an alpha source. After emitting alpha particle, it emits very low energy X-rays. Cobalt 60 is a beta source. Cobalt gets converted into nickel by emission of beta particles. After that, it emits two gamma rays, 1.17 MeV and 1.33 MeV gamma rays it emits. And then we have here strontium 90, which is also a beta source. Then we have sodium 22. Sodium 22 is a beta plus source. It is emitting right now positrons, antiparticles. They are colliding with the other electrons in the air molecules and converting them into two gamma rays of 511 keV each. So this source emits a beta plus, that is positron. After that, it emits a 1.22 MeV gamma ray, followed by that positron colliding and annihilating one of the electrons in the surrounding and producing two 500 keV gamma rays. These gamma rays enter here.
So at this point,
into this crystal, and they produce a process called scintillation, and this scintillation Scintillation is a process in which a high energy radiation will interact with the crystal and convert that energy into a photoelectron, high energy, and that electron then collides with the other electrons in the crystal and then excites the crystal modes and emits the whole energy in the form of ultraviolet and visible radiation, usually blue or ultraviolet radiation. This radiation then can be detected using a photomultiplier which sits behind this, which is given 1100 volts from here. That photomultiplier counts these photons in the form of, they converts them into electrons and amplifies them and gives you a voltage signal. The amplitude of the signal is proportional to the energy of the gamma ray, and that is recorded by this data acquisition system. So right now it is, what you are seeing here is the 511 keV gamma ray which is produced by the radioactive
And
decay.
here you have the number of counts.
Here is the amount, it is proportional to the energy, and this axis is the number of counts, vertical axis is the number of counts. So the voltage is not sufficient, so I'm going to increase this voltage and move the source also a bit closer. Okay, because I have to go now. So this peak is the 511 keV gamma ray. There will be a peak here which is coming due to the 1.22 MeV gamma ray, and this shape is coming, the background shape is coming due to a process called Compton effect. Compton effect makes sure that the gamma ray doesn't lose all the energy into the crystal, part of it escapes, and because of that you measure less energy than the full energy, and we will discuss that, and then you can use this for gamma ray spectroscopy. Okay, don't play around with these sources. I told them they are safe. That doesn't mean you should try to find out what is inside this. That will cause problem. Okay, don't unnecessarily point it towards people. It's not going to do anything, but it's possible that by mistake the person will touch this part, and that's not nice. Okay, so please. Yeah, that is the worst part of nuclear radiation. You see,
Means what will happen in this one?
cancer.
Cancer.
Diabetes is a
Okay. So you can see this will produce two peaks, and if you let it collect for some 5-10 minutes, you will see two peaks coming because this emits two gamma rays, and then this is the Compton background due to those gamma rays. Okay.
And here, sir, the peaks are there?
No, they will become. This is just a fluctuation, noise and all that, and of course Compton scattering effects and so on. So this is how basically this system.
Okay, they are
works.
starting becoming peaks.
Yeah. Okay, so you have to wait. You have to have patience.
So can we use the same detector for the X-rays?
Yes, but up to what energy?
From range to like 1 electron volt to 10 electron volts.
No, because the crystal inside is hygroscopic, so the crystal is covered using a very polished aluminum container. That container will not allow anything less than 5 keV to go inside.
Can we modify it according to that?
You can, but it's still a bulky system for flying in space. You're going to fit a Gaussian function here and here and get the resolution and get the Compton properties of this gamma ray. Okay. Please be careful with the source, and please be careful with.
This is the detector, no? Which is
this is the high voltage for the detector. This is the detector. Okay. Fine. Okay. Now, final thing. You are 22, so 11 in each batch, and we have 8 experiments. So obviously we have to have some sort of grouping to